The universe holds secrets that defy our basic understanding of reality. We are about to journey through 30 of the most profound mysteries in space, questions that leave even the most brilliant scientists without clear answers. This exploration will take you to the very edge of human knowledge, revealing the gaps in our cosmic map. You will discover why time might be an illusion and what truly lurks in the heart of a black hole. We stand at the frontier, peering into the darkness, and what we find there challenges everything. What part of the cosmos most sparks your own curiosity? That moment of creation, the Big Bang, is often described as the start of everything. But this leads us directly to our first great mystery, a question that seems so simple yet might be fundamentally unanswerable. What happened before the Big Bang? The problem lies in the nature of time itself. Our universe, with all its space and time, is thought to have burst into existence from an infinitely dense and hot point, a singularity. Time, as we understand it, is a property of our universe. It is the fabric against which events unfold. If the universe began with the Big Bang, then time itself began at that exact same moment. So asking what came before is like asking what is north of the North Pole. The question might not have any meaning within our current framework of physics. Yet the human mind rebels against this idea. We are wired to think in terms of cause and effect, of a sequence of events. How can something simply begin without a cause? This paradox has led scientists to propose some truly mind-bending alternatives. One compelling idea is the cyclic universe model, which suggests our universe goes through an endless series of big bangs and big crunches. In this view, our entire cosmos expands, then eventually contracts back down to a single point, only to explode outward once again in a new cycle. What we call the Big Bang was not the absolute beginning, but merely the latest rebirth in an infinite series. There was no before, only a previous cycle. Another radical theory points to the multiverse. Imagine our universe as just one bubble in a vast, foaming cosmic sea. This sea, a roiling quantum foam, continuously spawns new universes, each with its own unique laws of physics. Our Big Bang was simply the moment our particular bubble inflated. In this vast landscape, the question of what happened before our Big Bang transforms. It becomes a question of what is happening in the wider, meta-universe beyond our bubble's walls. Then there is the concept of a quantum fluctuation from nothing, where our entire universe could have simply popped into existence from a vacuum. A statistical inevitability given enough of whatever exists outside of existence. Each of these ideas stretches the limits of our comprehension, hinting at a reality far stranger than we can readily picture. This profound mystery of our cosmic origins connects to another enigma that permeates the very fabric of space. We can map its ghostly presence, we can measure its immense gravitational pull, yet we have no idea what it actually is. This is the puzzle of dark matter. Think of a spinning galaxy, a vast celestial pinwheel of stars and gas. According to the established laws of gravity, stars on the outer edges, farther from the galactic center, should orbit much more slowly than those near the core. Just as Pluto orbits our Sun far more sluggishly than Mercury. But when astronomers measured these galactic rotations, they found something startling. Stars on the fringes whip around at almost the same speed as those near the center. It is as if an invisible hand is holding the galaxy together, preventing these high-speed stars from simply flying off into the void. The visible matter, all the stars and glowing gas we can see, simply does not provide enough gravity to account for this motion. The only plausible explanation is that a huge amount of unseen matter, a kind of cosmic scaffolding, envelops every galaxy, exerting a powerful gravitational force. This is our primary evidence for dark matter. Another compelling clue comes from a phenomenon called gravitational lensing. Einstein predicted that massive objects warp the fabric of space-time, bending the path of light itself. We observe this when the gravity of a massive galaxy cluster acts like a giant lens, distorting and magnifying the light from even more distant galaxies behind it. The amount of bending we see is far greater than what the cluster's visible mass could possibly produce. Once again, an immense halo of invisible dark matter must be present, warping the light with its hidden gravity. So what could this mysterious substance be? It does not emit, absorb, or reflect any light, making it completely transparent. The leading theory suggests it is a sea of exotic particles that barely interact with normal matter. One candidate is known as WIMPs, or weakly interacting massive particles. These hypothetical heavy particles would flood the universe, passing right through our planet and our bodies without a trace, their only signature being their collective gravity. Another candidate is the action, a particle that is trillions of times lighter than an electron, but could exist in such staggering numbers that it accounts for the missing mass. For decades, scientists have built incredibly sensitive detectors deep underground, shielded from cosmic rays, hoping to catch the faintest whisper of a dark matter particle colliding with a normal atom. So far, the silence has been deafening. We are surrounded by this cosmic ghost, a substance that makes up roughly 85% of all the matter in the universe, and yet it remains utterly elusive, defining the structures we see while hiding in plain sight. If dark matter is the invisible glue holding galaxies together, then dark energy is the phantom force tearing the cosmos apart. While dark matter's gravity pulls, dark energy exerts a kind of repulsive gravity, a pressure that pushes space itself to expand at an ever-increasing rate. This discovery in the late 1990s was so shocking it completely overturned our picture of the universe's fate. Astronomers were observing a specific type of stellar explosion in incredibly distant galaxies, a standard candle known as a Type I, a supernova. By measuring how much dimmer these explosions appeared, they could calculate their true distance. They could also measure how fast these galaxies were moving away from us by the reddening of their light. The expectation was that the expansion of the universe, set in motion by the Big Bang, should be slowing down over time due to the relentless pull of gravity from all the matter in the cosmos. But the data revealed the opposite. The most distant supernovae were fainter than they should have been, meaning they were farther away than anyone had predicted. The expansion of the universe was not slowing down at all. It was speeding up. Some mysterious, unknown force was counteracting gravity and driving the galaxies apart faster and faster. This was the first direct evidence for dark energy. The leading explanation points to a property of empty space itself. In Einstein's equations, there is a term called the cosmological constant, representing a constant energy density that fills the vacuum of space. Think of empty space not as a true void, but as a seething quantum foam where virtual particles constantly flicker in and out of existence. This activity gives the vacuum a fundamental energy, and according to this idea, that energy has a repulsive gravitational effect. Imagine our dots on the surface of a balloon, each dot a galaxy. Now picture someone not just steadily inflating the balloon, but blowing into it with more and more force. The dots rush away from each other at an accelerating pace. That is the effect of dark energy. Yet this simple idea creates a colossal problem for physics. When theorists try to calculate the expected strength of this vacuum energy using quantum mechanics, the number they get is wrong by a factor of 1 followed by 120 zeros. It is the worst theoretical prediction in the entire history of science. This staggering failure tells us we are fundamentally missing something profound about the nature of space, energy, and gravity. Dark energy, making up about 68% of the universe, is not just an invisible component. It is the dominant force shaping our cosmic destiny, and we have no real idea what it is. This staggering void in our understanding of what drives the cosmos leads to a question that feels deeply personal. With billions of galaxies, each containing trillions of planets, the sheer number of worlds is beyond human comprehension. The statistics scream that life should be common, that the cosmos should be buzzing with activity. Yet when we listen, we are met with an eerie, profound silence. This contradiction is the heart of the Fermi paradox, a mystery that asks a simple, haunting question. Where is everybody? The numbers are overwhelmingly in favor of life. In our Milky Way alone, there are an estimated 100 billion planets. Many of these orbit within their star's habitable zone, that Goldilocks region where temperatures are just right for liquid water, a key ingredient for life as we know it. Given these staggering odds, it seems statistically inevitable that life has arisen elsewhere. So why do we see no signs of great galactic empires, no interstellar messages, no visitors? This silence suggests there is a barrier, a cosmic checkpoint that is incredibly difficult to pass. This idea is known as the Great Filter. It proposes that at some point between the initial conditions for life and the emergence of a spacefaring civilization, there is a step so unlikely, so treacherous, that it effectively filters out almost every candidate. The terrifying question is where this filter lies. Is it behind us or is it still ahead? If the filter is in our past, it means we have already overcome an almost insurmountable obstacle. Perhaps the origin of life itself from non-living chemistry is an astronomically rare fluke. Or maybe the leap from simple single-celled organisms to complex multicellular life is the true bottleneck. In this hopeful scenario, we are among the first or the only to have made it this far, and the galaxy is ours to explore. The far more unsettling possibility is that the Great Filter lies in our future. Perhaps the development of advanced technology inevitably leads to self-destruction. The moment a species gains the power to alter its planet or create powerful weapons, it succumbs to its own hubris, war, or ecological collapse. This would mean that the silence we hear is a graveyard, a universe filled with the ghosts of civilizations that burned out just as they were poised to reach for the stars. Another possibility is that intelligence itself is a kind of trap, where species become consumed by virtual realities or other internal pursuits, losing all interest in the physical universe beyond their atmosphere. We are left staring at the stars, wondering if the great silence is a warning or simply the quiet before we find our own voice. This profound silence surrounding the existence of others forces us to look not just outwards but also forwards to the ultimate destiny of everything we see. The fate of the entire cosmos hinges on a delicate balance between the outward push of dark energy and the inward pull of gravity. Based on the precise density of the universe, scientists have envisioned three dramatic endings, each more final than the last. The first is the Big Crunch, a cosmic reversal of the Big Bang. In this scenario, the collective gravity of all the matter in the universe is finally strong enough to overcome the expansion, slowly putting on the brakes. Galaxies would begin to fall back toward each other, space itself would contract, and the temperature would rise. The universe would rush toward a fiery, catastrophic collapse, crumpling back into the singularity from which it began, perhaps setting the stage for a new cycle. The second, and currently the most supported by our observations, is the Big Freeze or heat death. Here, dark energy maintains its dominance, driving the universe to expand forever at an accelerating rate. Over trillions of years, the last stars will exhaust their fuel and wink out of existence. Galaxies will drift apart into an ever-cooling, ever-darkening void. Even the building blocks of matter themselves, protons and neutrons, may not be stable, eventually decaying into radiation. The universe would approach a state of absolute cold, absolute darkness, and absolute equilibrium, where no energy can be transferred and no new event can ever occur again. It is the ultimate, irreversible silence. The third possibility is the most violent of all, the Big Rip. This scenario depends on dark energy not just being constant but growing stronger over time. If this phantom energy's repulsive force intensifies, it would eventually overwhelm every force that holds things together. First, galaxy clusters would be torn apart. Then, individual galaxies. As the end nears, the fabric of space would expand so violently that it would rip stars from their planetary systems. In the final moments, even atoms would be shredded, followed by the very nuclei of atoms, and finally, space-time itself would be torn asunder. The universe would end not with a whimper, but with a catastrophic, instantaneous rupture. Our current measurements of the accelerating expansion point most strongly toward the Big Freeze, a slow, cold, and lonely end. Yet the true nature of dark energy remains the great unknown variable. A single new discovery about its properties could tilt the scales, sealing our cosmic fate toward a fiery collapse or a violent disintegration. We are left watching the expansion, trying to read our ultimate destiny in the faint glow of distant, fleeing galaxies. These cosmic endings, whether a freeze or a rip, are defined by the ultimate power of gravity. And nowhere is gravity's hold more absolute than in a black hole. Crossing its boundary, the event horizon, means leaving the known universe behind. This is not a physical surface you can touch, but a one-way door in space-time. Once an object passes this invisible threshold, the gravitational pull becomes so immense that not even light, the fastest thing in existence, can achieve escape velocity. The black hole's interior is forever sealed from our view. According to our best understanding of general relativity, all matter that falls in is crushed and funneled downward to the very center, toward a point called the singularity. Here, the predictions of physics become nonsensical. Density and gravity are thought to become infinite. The very fabric of space and time is shredded. Our equations simply break down, offering no answers, only a profound sign that says, "Here be dragons." This classical view, however, creates one of the most vexing puzzles in modern physics, the black hole information paradox. In the quantum world, information is never truly lost. If you burn a book, the information contained in its letters seems destroyed. But in principle, if you could collect every single smoke particle and trace the precise energy released, you could theoretically reconstruct the book. The information is scrambled, but it is conserved. A black hole appears to violate this fundamental principle. When an object falls in, all the information about what that object was, its composition, its structure, its history, seems to vanish from our universe, trapped forever behind the event horizon. Even worse, Stephen Hawking showed that black holes are not completely black. They slowly evaporate over astronomical timescales by emitting a faint glow of radiation. But this Hawking radiation is purely thermal. It carries no information about what fell in. So if a black hole eventually evaporates completely, what happened to all that information? It seems to be permanently erased from reality, a clear contradiction of quantum law. To resolve this paradox, physicists have been forced to consider truly radical ideas. One of the most compelling is the holographic principle. It proposes that all the information about everything that falls into a three-dimensional black hole is not lost inside, but is instead encoded on a two-dimensional surface, painted onto the event horizon itself like a cosmic hologram. Imagine the stunning visualizations from films like Interstellar, where the black hole gargantua is depicted with a luminous, swirling disk of matter. The holographic principle suggests that the true reality of what is inside is not a chaotic crush of matter, but a perfect, ordered record imprinted on its shimmering boundary. Simulations of matter falling into a black hole show it stretching and distorting, a process known as spaghettification before it crosses the horizon. According to this new view, its information is simultaneously smeared and copied onto the event horizon, preserved forever even as the object itself passes into the unknown. This idea forces us to reconsider the nature of reality itself. Is our perception of a three-dimensional universe merely an illusion, a holographic projection from a two-dimensional surface at the edge of the cosmos? The black hole, an object of pure destruction, might be the key that unlocks this deepest of secrets. That holographic view of reality suggests the cosmos might be far stranger than a single, self-contained entity. This leads us to a question that pushes the boundaries of science itself. Is our universe just one page in an infinite cosmic library, a single bubble in a vast, foaming multiverse? The idea of multiple universes is not just science fiction. It emerges naturally from several of our most advanced yet incomplete theories of physics. One of the strongest arguments comes from cosmic inflation, the theory that our universe underwent a fantastically rapid expansion in its first fleeting moments. Some versions of this theory suggest this inflation never truly stops. Instead, it continues eternally. Picture a constantly bubbling pot of water or a cosmic bubble bath. The background space, the water itself, is forever inflating, but within it, random quantum fluctuations cause pockets to stop inflating and pinch off, each one becoming its own separate universe with its own Big Bang. Our entire observable cosmos is just one such bubble in an endless, ever-growing froth. Within this inflationary multiverse, the fundamental constants of nature could be different in each bubble. In one universe, the force of gravity might be stronger. In another, the nuclear forces that hold atoms together might be weaker, preventing stars from ever forming. We just happen to live in a bubble where the numbers are perfectly tuned for our existence, a concept known as the anthropic principle. String theory, a candidate for a theory of everything, adds another layer to this. It suggests the number of possible stable configurations for the extra dimensions it proposes is astronomically large, perhaps 10 to the power of 500. Each of these configurations would manifest as a universe with a different set of physical laws. This is known as the string theory landscape, and it paints a picture of a multiverse of almost limitless variety. Then there is the truly mind-bending idea from quantum mechanics, the many worlds interpretation. Every time a quantum event has multiple possible outcomes, the universe does not choose one. Instead, it splits. In one branch, a radioactive atom decays. In another, it does not. Every possible outcome of every quantum interaction is realized in its own separate, equally real world. In this view, a near-infinite number of parallel versions of history are constantly branching off from our own. But are these scientific theories or untestable philosophy? The greatest challenge is that by definition, these other universes are likely forever beyond our observational reach. Their light can never reach us, and we can never interact with them. How can we prove something we can never see? Scientists are searching for indirect evidence. Perhaps our universe once collided with another bubble in the multiverse, leaving a unique imprint on the cosmic microwave background, the afterglow of the Big Bang. Or maybe the specific pattern of gravitational waves from the early universe will reveal clues about the inflationary process that spawned the multiverse. For now, the multiverse remains a powerful, provocative idea. It solves some puzzles, like why our universe seems so finely tuned for life, but it raises a profound question about the nature of science itself. If a theory predicts an infinite number of universes we can never observe, has it moved from physics into the realm of metaphysics? The same quantum processes that may spawn entire universes could also have set the stage for life's first spark right here on our own planet. How did inanimate matter cross the threshold into life? This leap from chemistry to biology is known as abiogenesis, and it remains one of nature's most guarded secrets. The fundamental challenge is immense. Life, even in its simplest single-celled form, is staggeringly complex. It requires a system that can metabolize energy, maintain a boundary from its environment, and most crucially, replicate itself. Getting this entire system to self-assemble from a primordial soup of simple chemicals seems almost like a miracle. Yet, experiments have shown that the first steps on this long road are not only possible but probable. In the 1950s, Stanley Miller and Harold Urey recreated the suspected conditions of early Earth in a glass apparatus. They filled it with water, methane, ammonia, and hydrogen, gases thought to make up the primitive atmosphere. Then they passed electrical sparks through the mixture, simulating lightning. In just a week, the clear water turned a murky pink, and analysis revealed that something remarkable had happened. The experiment had produced several amino acids, the fundamental building blocks of proteins, which are essential for all known life. This was a landmark discovery, proving that the basic ingredients for life could form spontaneously from simple conditions. But making the bricks is a long way from building the cathedral. The next great hurdle is understanding how these building blocks assembled into more complex structures, and most elusively, how the first self-replicating molecule emerged. Many scientists now believe the first spark of life did not occur in a warm little pond, but in the deep, dark ocean. At hydrothermal vents on the seafloor, superheated, mineral-rich water spews from chimneys into the cold depths. These environments provide a constant source of energy and a rich gradient of chemicals, all within the protective pores of the rock. Here, the earliest metabolic processes might have begun, perhaps even before the emergence of genetics. The leading candidate for that first self-replicator is a molecule called RNA. Unlike DNA, which is a passive blueprint, RNA can act as both a store of information and a catalyst for chemical reactions. It can, in a sense, copy itself. The discovery that RNA can drive its own replication in the lab offers a compelling pathway for how a molecule could have transitioned from mere chemistry to a primitive form of biology, kickstarting the evolutionary process. Yet another possibility pushes the origin of life beyond our world entirely. This is the concept of panspermia, the idea that life's seeds, or at least its complex organic precursors, are common throughout the cosmos, hitchhiking on asteroids, comets, or interstellar dust. We know that meteorites falling to Earth are rich in amino acids and other organic compounds. It is plausible that a constant rain of these materials early in Earth's history delivered a starter kit, significantly enriching the primordial soup. The more radical version suggests that hardy, microscopic organisms could survive the long, dark journey through space, shielded within the interiors of rocks, seeding life on any habitable world they encounter. If true, we may all be descendants of cosmic travelers. So did life begin in the deep sea vents of a young Earth, or did it arrive from the depths of space? The answer might be a combination of both, with the cosmos delivering the raw materials and our planet's unique environments providing the workshop for assembly. This mystery connects our own existence directly to the wider universe, suggesting that the story of life is inextricably woven into the story of the cosmos itself. This connection between life and the cosmos forces us to question a more fundamental aspect of our reality, the very flow of time itself. Is time a genuine river carrying us from past to future, or is it merely a powerful illusion constructed by our minds? Physics offers a startling answer that challenges our deepest intuitions. The block universe theory suggests that past, present, and future are not sequential. They all exist simultaneously, laid out eternally across the four-dimensional fabric of space-time. Imagine the entire history of the universe as a finished movie on a reel. We are like a projector light moving frame by frame, experiencing each moment as now. But the frames representing your birth, your life, and even the distant future of the cosmos are all equally real and already there. The flow of time is just our conscious journey through this static block. This view emerges directly from Einstein's theory of relativity, which showed that time is relative and can stretch and compress. There is no universal now that all observers can agree on. Your present moment and the present moment for an astronaut orbiting a distant star are not the same. The distinction between past and future loses its absolute meaning. So why does time feel so unshakably real and directional to us? the answer may lie not in the fundamental laws of physics, but in a concept from thermodynamics called entropy. Entropy is a measure of disorder, and the second law of thermodynamics states that in any closed system, the total entropy always increases over time. Think of a new deck of cards perfectly ordered. If you shuffle it, the deck becomes disordered, and it is incredibly unlikely to ever randomly return to its original sequence. The universe is like that deck of cards. It began in a state of incredibly low entropy, a highly ordered and dense state at the Big Bang, and has been moving toward greater disorder ever since. This relentless increase in entropy gives us the arrow of time. We remember the past because it was more ordered, and we move into a future of increasing disorder. A broken cup shatters and does not reassemble itself because that would mean a spontaneous and fantastically improbable decrease in entropy. Our very consciousness, the process of forming memories and experiencing change, seems to be tied to this one-way march of the cosmos toward chaos. The great mystery is why the universe started with such low entropy in the first place. What set this cosmic clock ticking? The answer remains one of the most profound puzzles, suggesting that the true nature of time is woven into the initial conditions of reality itself, a secret buried in the first moment of existence. Our very existence is a cosmic defiance of a fundamental rule. The laws of physics, as we currently understand them, insist that the Big Bang should have created perfect counterparts, equal amounts of matter and antimatter. For every particle of matter, like an electron or a quark, there should have been a mirror image particle of antimatter with the same mass but opposite charge. And when matter and antimatter meet, they annihilate each other in a flash of pure energy, leaving nothing behind. This means the entire universe should have cancelled itself out in the first microseconds of its life, leaving a vast, featureless sea of radiation. Yet here we are, made of matter, in a universe filled with galaxies, stars, and planets. Something must have broken the perfect symmetry. A tiny, 1 in a billion imbalance must have tipped the scales, allowing a small surplus of matter to survive the great annihilation. This mystery is known as baryogenesis, the genesis of the matter that makes up everything we see. Physicists are hunting for the specific physical process that caused this violation of symmetry. The leading suspect is a phenomenon known as CP violation, which stands for charge and parity. In simple terms, it means that the laws of physics treat particles and their antiparticles slightly differently, and they also treat a process differently from its mirror image. This tiny bias in the early universe could have been the mechanism that favored matter over antimatter. Experiments at facilities like CERN are trying to recreate these first moments by smashing particles together at nearly the speed of light. Deep underground in massive detectors, they observe the debris of these collisions, searching for any hint that certain particles and their antiparticles decay at slightly different rates. This would be the smoking gun, the evidence of a fundamental crack in the mirror of nature. Visualize it like a vast cosmic coin toss at the beginning of time. The universe flipped a coin, and for matter to win and for us to be here, the coin had to be ever so slightly weighted. Finding that weight, that specific broken symmetry, is not just about understanding a particle physics puzzle. It is about answering the most fundamental question of all. Why is there something rather than nothing? That matter-antimatter imbalance gave us a universe to exist in, but what is the true nature of this cosmic arena itself? We can measure the observable universe, the sphere of light that has had time to reach us since the Big Bang, but this is just our limited view. The full extent of the cosmos, its true size and shape, remains one of its most fundamental mysteries. Is everything we see merely a tiny island in an infinite sea, or is the universe finite, a closed structure with a definite volume? Our best measurements point to a surprising and almost unsettling answer. The geometry of the universe appears to be flat. This does not mean it is shaped like a sheet of paper, but that on the largest scales, the rules of Euclidean geometry we learned in school hold true. Parallel lines will never meet, and the angles of a triangle always add up to 180 degrees. A flat geometry, according to the equations of general relativity, most naturally implies an infinite universe. It would stretch on forever with no edge, containing an endless number of galaxies, stars, and perhaps even copies of you. The sheer scale of that idea is enough to make anyone feel dizzy. Yet there is another, equally mind-bending possibility. The universe could be finite but unbounded. The classic analogy is the surface of the Earth. Our planet has a finite surface area, but you can walk in any one direction forever without ever reaching an edge. The universe could be similar, but in 3 dimensions. Its geometry could be flat, but its topology, its overall connectivity, could be wrapped in on itself. One of the leading candidates is a 3-dimensional torus, like the surface of a donut, but with all the dimensions inflated to a cosmic scale. If you could travel in a perfectly straight line in such a universe, you would eventually return to your starting point from the opposite direction, having circumnavigated the entire cosmos. How could we ever hope to detect such a shape? The key might lie in the oldest light in the universe, the cosmic microwave background. This faint afterglow from the Big Bang fills all of space, and it carries an imprint of the universe's structure when it was just a baby. If the cosmos is finite and wrapped like a hall of mirrors, the light from one extremely distant object could have taken multiple paths to reach us. Scientists are meticulously scanning this cosmic background radiation, searching for matching circles, identical patterns of hot and cold spots that appear in multiple places on the sky. Finding such a repeating pattern would be like seeing the same mountain range from 2 different windows in a vast curved mansion, proving that the universe is finite and revealing its true hidden topology. The search continues, sifting through the faint whispers of creation, hoping to find a signature that tells us whether we live in an endless expanse or a colossal but closed cosmic loop. This question strikes at the very limits of causality. We have traced the universe back to an infinitely dense point, a singularity governed by no known laws of physics, and we are forced to ask what could possibly have set it in motion. The Big Bang describes the hot, dense state that followed the beginning of expansion, but it does not explain the initial kick. The leading scientific idea for that kick is cosmic inflation. Picture the entire observable universe, all 100 billion galaxies, compressed into a space far smaller than a single atom. In the first sliver of a second, a minuscule fraction of a heartbeat, this subatomic speck underwent a staggering exponential expansion, inflating faster than the speed of light itself. This was not an explosion into space, but a violent stretching of space. In that fleeting moment, a region of space smaller than a proton was blown up to a size larger than our entire observable cosmos today. This inflationary theory elegantly solves several major puzzles, like why the universe is so uniform in all directions and why its geometry appears so perfectly flat. Yet it immediately raises a deeper mystery. What powered this incredible burst of expansion? The proposed engine is a hypothetical field called the inflaton. Think of it as a strange, high-energy cousin to the Higgs field that gives particles their mass. In the earliest moment, this inflaton field was trapped in a state of false vacuum, a high-energy configuration that imbued empty space with a powerful repulsive gravity, forcing it to expand at a fantastic rate. As the field slowly decayed and relaxed to its true, lower energy state, that colossal energy had to go somewhere. It was dumped into the fabric of the universe, heating it into the primordial fireball of the Big Bang, creating all the matter and radiation we see today. But this just pushes the mystery back one step. We do not know what the inflaton field actually is, or what set it up in that unstable state to begin with. To grasp the sheer brevity of this event, imagine the entire 14 billion-year history of the universe compressed onto a single logarithmic timeline. On this scale, all of recorded human history would be smaller than the blink of an eye at the very end. the entire reign of the dinosaurs would be a tiny speck. The formation of our solar system, a slightly larger mark, yet the entire inflationary epoch, the event that set the entire cosmic stage, would occupy a span so infinitesimally small it would be virtually invisible, a ghost at the very beginning of time. So what existed before inflation, or before the singularity it emerged from? One of the most profound speculations is that our universe is the product of a quantum fluctuation. In the bizarre world of quantum mechanics, empty space is not truly empty. It is a seething, probabilistic foam where pairs of virtual particles constantly pop into and out of existence, borrowing energy from the vacuum for a fleeting moment before annihilating each other. Perhaps our entire cosmos is the ultimate quantum fluctuation, a bubble of space-time that simply popped into being from nothing, a statistical inevitability in an eternal, metaphysical void. In this view, the question of what caused the Big Bang transforms. It becomes a question of why there is a quantum law that allows for something to come from nothing at all. The quantum foam from which our universe may have bubbled hints at a reality far more expansive than three simple directions. We are intimately familiar with the three dimensions of space: length, width, and height, the full freedom to move forward, sideways, and upward. Yet, some of our most promising theories for unifying all the forces of nature suggest this is only a fraction of the full story. The mathematics of string theory, for instance, only achieves its beautiful, unifying consistency in a universe with 10 or 11 dimensions. This raises a baffling question. If they exist, where are these extra dimensions and why do we not experience them? The leading explanation is a process called compactification. Imagine a single, long garden hose stretching far into the distance. From a great distance, it appears to be a simple one-dimensional line, but an ant crawling on its surface would discover a second dimension, the circular path around the hose's tube. This tiny, curled-up dimension is always there, but it is invisible to anyone not looking closely enough. In the same way, the 6 or 7 extra dimensions required by string theory could be curled up into an impossibly small, complex shape at every single point in our familiar three-dimensional space. These Calabi-Yau manifolds, as they are known, are so fantastically tiny, perhaps at the Planck scale of a trillionth of a trillionth of a trillionth of a meter, that they are completely hidden from our everyday perception. Every time you move your hand through the air, you are swirling through a hidden, 6-dimensional labyrinth of unimaginable complexity, all curled up into a size far smaller than any particle we can detect. How could we ever hope to find evidence for such a fantastical idea? One possibility lies in the world's most powerful particle colliders. When scientists smash protons together at nearly the speed of light, they are recreating the energy conditions of the very early universe. In these violent collisions, it is theorized that some of the energy produced could literally disappear into one of these hidden dimensions, carried away by a particle that has access to the full spatial reality. Our detectors would simply register a mysterious loss of energy, a violation of the conservation laws, pointing to a leak into the wider cosmos. Another clue might come from gravity, the weakest of the fundamental forces. Its incredible feebleness compared to electromagnetism or the nuclear forces has always been a puzzle. One compelling explanation is that gravity is not weak at all. It is simply diluted, while the other forces are confined to our three-dimensional membrane of space-time. Gravity, as the curvature of space itself, might be the only force that can seep into these extra dimensions. Its strength spreads out across the full 10-dimensional bulk, so that by the time we feel its pull in our three-dimensional world, it is only a faint shadow of its true power. If these extra dimensions exist, they would redefine our place in the cosmos. We would not be living in a universe of vast, empty space, but on a three-dimensional island, a brain, floating within a much richer, higher-dimensional reality, a concept that transforms the very meaning of here. The very structure of reality might be woven with dimensions we cannot perceive, but what about the inner world of experience itself? Consciousness is the most intimate and baffling mystery, the bright flame of awareness that allows us to even ponder these cosmic questions. We know it arises from the intricate network of our own brains, but is it merely a biological accident, or could it be a fundamental feature of the cosmos? This question shatters the boundary between space science and deep philosophy. If we are searching for other minds in the universe, we must first ask what a mind truly is. The traditional scientific view holds that consciousness is an emergent property, a complex software that runs on the wetware of the brain. Billions of neurons firing in a specific pattern somehow generate the feeling of the color red, the taste of chocolate, the ache of sadness. In this view, any system complex enough, whether a sophisticated alien brain or a future artificial intelligence, could, in principle, become conscious. But this leads to a profound puzzle known as the hard problem of consciousness. We can map every neural pathway, we can understand the physics of every synapse, but we can never explain why all that electrical and chemical activity is accompanied by a subjective inner experience. Why is there something it is like to be you? This gap in our understanding has led some philosophers and scientists to a radical alternative, panpsychism. This idea suggests that consciousness is not a late-arriving product of complexity, but a fundamental property of matter as basic as mass or charge. In this view, even an electron might possess a tiny, primitive spark of experience, a single note of feeling. In simple particles, this consciousness would be incredibly simple and fragmented, but in highly complex systems like the human brain, these countless micro-experiences combine and unify into the rich, flowing stream of awareness we all know. It is a provocative thought that the universe might not be a dead, mechanical place, but is in some sense awake all the way down. If panpsychism, or something like it, is true, then the potential for consciousness is woven into the fabric of reality itself. It could arise in forms utterly alien to our own. How would we recognize intelligence if it were not housed in a carbon-based brain? Imagine a vast, sentient gas cloud drifting between the stars, its thoughts unfolding over millennia as slow gravitational tides. Or consider a planet-spanning fungal network communicating and processing information through chemical signals in the soil, its mind a patient, rooted intelligence. Our most advanced artificial intelligences might already be treading the borderlands of sentience. If a complex AI running on silicon rather than neurons began to express curiosity, fear, or a desire for self-preservation, would we even believe it? Or would we dismiss its pleas as clever programming? This radically reframes the search for extraterrestrial intelligence, or SETI. For decades, we have been listening for narrow-band radio signals, a technology we ourselves developed. We are looking for a mirror of our own technological adolescence, but if consciousness is a universal potential, the signs of its presence might be far stranger and more subtle. We might not be searching for a message, but for a mind that has merged with its environment, a civilization that has become a planetary consciousness, its thoughts imprinted on the global climate or the patterns of its star's energy output. The great silence we perceive might not be emptiness at all, but a chorus of minds so different from our own that we lack the senses to hear them. Our own galaxy is racing through the cosmos at a breathtaking speed, pulled by a force we cannot see. This mysterious source of gravity is known as the Great Attractor, and it represents one of the most formidable puzzles in our cosmic backyard. It is a colossal gravitational anomaly, a single point in intergalactic space with the mass of tens of thousands of galaxies, tugging on our Milky Way and every other galaxy in our local supercluster. We are all flowing in a vast river of galaxies toward this unseen destination, but the greatest frustration for astronomers is its location. It lies directly behind the central bulge of our own galaxy, in a region of the sky we call the zone of avoidance. This area is completely obscured by thick clouds of cosmic dust and the brilliant, crowded stars of the Milky Way's core. It is like trying to see a distant city through a dense, perpetual fog. For decades, this zone was a literal blind spot, hiding what could be one of the most massive structures in our local universe. How do you study something you cannot see? Scientists had to turn to instruments that peer through the dust, using radio waves and X-ray telescopes to map the hidden landscape. What they found was both an answer and a deeper mystery. The pull we feel is not from a single, monstrous object, but from an immense concentration of mass known as the Norma cluster, a rich gathering of galaxies that forms the heart of the larger Laniakea supercluster, our home on the grandest scale. This supercluster, a vast cosmic filament containing over 100,000 galaxies, is the true source of the gravitational pull. Yet, even this colossal structure may not fully account for the entire motion we observe. There are hints that something even larger and more massive lies behind the great attractor, pulling on the puller itself. This could be the Shapley supercluster, the most massive known concentration of galaxies in our observable universe, exerting its own immense gravitational influence from an even greater distance. So the journey does not end with the great attractor. It is merely a waypoint, a signpost on a much longer cosmic migration. We are being drawn not toward a single point, but along an invisible current in the ocean of spacetime, flowing toward the densest concentrations of matter in our corner of the cosmos. This hidden geography reminds us that our view of the universe is still profoundly limited, and that the darkest patches on our maps often hold the greatest secrets. These cosmic currents are mapped by the faint whispers of ancient light, but sometimes the universe shouts. Without warning, a point in the sky erupts, releasing in a single millisecond more energy than our sun puts out in 3 days. This is a fast radio burst, one of the most intense and perplexing phenomena in the cosmos. These blasts of radio waves travel across billions of light years, a fleeting, powerful scream in the dark. The first one was discovered only in 2007, buried in archival data from a radio telescope, and since then we have detected hundreds. Their brevity is what makes them so difficult to study. They appear as a sudden, brilliant spike on a radio frequency chart, a vertical line that rises and falls almost instantly, and then they are gone. Catching one as it happens is like trying to capture a single frame in a movie playing at lightning speed. The mystery deepens with the discovery that not all of these bursts are the same. Some are lone events, a single, catastrophic boom from a distant galaxy that never repeats. Others are repeaters, sending out multiple bursts from the same location, sometimes in a predictable pattern, sometimes at random. This fundamental difference suggests there might be at least 2 distinct cosmic engines powering these incredible explosions. The leading suspect for at least some of these bursts, especially the repeaters, is a type of stellar corpse called a magnetar. Imagine a neutron star, the ultra-dense remnant of a supernova, crushed into a sphere just a few miles across but containing the mass of a star. Now take that object and give it a magnetic field 1,000 trillion times more powerful than Earth's. This is a magnetar. The magnetic stresses on its surface are so immense that they can cause starquakes, violent ruptures in the crust that release colossal flares of energy, potentially in the form of a fast radio burst. We have even detected a tremendously powerful radio burst from a magnetar within our own galaxy, providing the first solid link between these exotic objects and the phenomenon. But for the one-off, non-repeating bursts, the story may be different. These could be the signature of the most violent events in the universe. The collision and merger of 2 neutron stars, for instance, could unleash a final, concentrated pulse of radio energy as the objects spiral into each other. Or perhaps it is the birth of a black hole, a singular moment of creation that announces itself with a radio blast before settling into silence. Then there are the more speculative ideas. Could these focused, incredibly energetic signals be evidence of alien technology? The power required to send such a signal across intergalactic space is almost unimaginable, perhaps harnessing the energy of an entire star. An advanced civilization might use a powerful beacon like this for propulsion, for communication, or for purposes we cannot even conceive. While natural explanations are far more likely, the sheer intensity and mystery of these bursts force us to at least consider the possibility. The true nature of fast radio bursts remains locked within that millisecond flash. Each new detection is another piece of a cosmic puzzle, a clue to the most energetic and secretive processes at work in the depths of space. The sheer violence of fast radio bursts reveals a cosmos of immense power and chaos, a universe that seems overwhelmingly hostile to fragile things like us. And yet, here we are, existing in a realm that appears to be perfectly calibrated for our presence. This leads to one of the most profound questions of all. Why is the universe so exquisitely tuned for life? The fundamental constants of nature, the numerical values that govern the strength of every force and the mass of every particle, seem to be set with impossible precision. If any one of them were even slightly different, the cosmos as we know it would not exist. Consider the force of gravity. If it were just a little bit stronger, the universe would have collapsed back on itself in a big crunch long before stars ever had a chance to form. If it were slightly weaker, matter would never have clumped together to form galaxies or stars in the first place. The universe would be a cold, thin, and perpetual haze of hydrogen gas. The nuclear forces are even more delicate. The strength that binds protons and neutrons together in an atom's nucleus has a very specific value. If it were marginally weaker, a single proton could not bond to a neutron, and the simplest elements like deuterium would never form. There would be no complex atoms, no chemistry, and no planets. If the strong nuclear force were slightly stronger, two protons could stick together directly, bypassing the need for neutrons. This would cause all the hydrogen in the early universe to fuse into helium almost instantly, burning out the fuel for stars like our Sun before life could ever emerge. Even the mass of a proton seems fine-tuned. A proton is slightly lighter than a neutron. If their masses were reversed, neutrons would not decay into protons, and the universe would be filled with neutron stars and black holes instead of stable atoms. Everywhere we look, we find this same razor's edge balance. It is as if the universe has dozens of independent dials, and every single one is set to an exact value that allows for galaxies, stars, planets, and ultimately observers. This remarkable observation is known as the fine-tuning problem. So how do we explain this incredible luck? One compelling answer is the anthropic principle. In its simplest form, it states that we can only observe a universe that is capable of supporting our existence. We are here to ask the question because the conditions are right for us to be here. This idea connects directly to the concept of the multiverse. If an infinite number of universes exist, each with its own random set of physical constants, then it is no surprise that we find ourselves in one of the vanishingly few where the numbers just happen to come out right. In this view, there is no deeper reason for the fine-tuning. We simply won the cosmic lottery. The alternative is that there is a deeper, unified law of physics that we have not yet discovered, a single principle that determines why all the constants must have the values they do. Perhaps they are not freely adjustable dials at all, but are locked together in a necessary mathematical relationship. Finding such a theory of everything would show that the universe could not have been any other way, that life is not a lucky accident but an inevitable consequence of the fundamental logic of reality. For now, we are left with two staggering possibilities. Either we live in a solitary, inexplicably perfect universe, or we are one tiny voice in an infinite cosmic choir, a statistical inevitability in a sea of lifeless chaos. The answer will define not only our place in the cosmos, but the very nature of existence itself. these subatomic bullets strike our sky with a force that defies belief. They are ultra-high-energy cosmic rays, atomic nuclei traveling at nearly the speed of light, each one carrying the punch of a professionally thrown baseball, all compressed into a single, invisible particle. This is millions of times more energy than we can generate in our most powerful particle colliders. They arrive randomly from the depths of space, and when one of these rare projectiles slams into the upper atmosphere, it triggers a spectacular cascade. The primary particle collides with an air molecule, shattering into a shower of secondary particles, which then collide and create more, raining down a fleeting, invisible avalanche of energy over several square miles. We only know of their existence through the intricate grids of detectors that cover vast tracts of land, waiting to capture the faint echoes of these cosmic bombardments. The central mystery is not their power but their origin. The universe is crisscrossed with magnetic fields which act like a hall of mirrors for these charged particles. A proton or an atomic nucleus carrying a positive charge does not travel in a straight line. It gets bent and twisted, sent on a chaotic, spiraling path by every magnetic field it encounters along its billion-year journey. By the time it reaches us, its trajectory is a tangled mess, completely obscuring the direction of its source. It is like trying to find the origin of a leaf that has been blown by 1,000 different winds before finally landing in your yard. So what cosmic engines are capable of launching such devastatingly powerful particles? The suspects are the most violent objects in the universe. One prime candidate is the active galactic nucleus, the supermassive black hole at the heart of a distant galaxy, greedily feeding on surrounding matter. As material is torn apart and accelerated to relativistic speeds in the black hole's powerful jets, it could act as a natural particle accelerator of unimaginable scale, flinging atomic nuclei across the cosmos. Another possibility is the aftermath of a gamma-ray burst, the most energetic explosion since the Big Bang itself. The collapsing core of a massive star or the merger of two neutron stars could create shock waves powerful enough to inject particles with these incredible energies. Scientists have tried to solve this mystery by creating maps of the sky, plotting the arrival directions of the very highest energy cosmic rays. These maps do not show a uniform scatter. Instead, they hint at faint hotspots, potential sources located in regions of the sky devoid of any obvious, violent objects. This only deepens the puzzle, suggesting that the true sources could be something we have not yet identified, or that our understanding of how particles travel through the intergalactic medium is fundamentally flawed. We are being shot at by an invisible sniper, and we cannot even figure out which direction the bullets are coming from. These cosmic bullets, with their unimaginable energy, are governed by two sets of rules that refuse to speak to one another. The immense violence of their sources is described by Einstein's general relativity, the physics of the very large, while the particles themselves are ruled by the bizarre laws of quantum mechanics, the physics of the very small. Unifying these two pillars of physics into a single theory of quantum gravity is perhaps the greatest challenge in all of science. General relativity paints a beautiful picture of gravity as the curvature of spacetime. A massive object like the Sun creates a dip in the cosmic fabric, and planets simply follow the curves of this warped geometry. It is a smooth, continuous landscape. Quantum mechanics, however, reveals a world that is grainy, probabilistic, and fundamentally chaotic. Particles pop in and out of existence, and forces are carried by discrete packets of energy called quanta. We have quantum theories for electromagnetism and the nuclear forces, but gravity has stubbornly resisted this treatment. To understand the most extreme environments in the universe, like the core of a black hole or the very first moment of the Big Bang, we desperately need a theory that can describe how gravity behaves at this tiny quantum scale. In these places, the curvature of spacetime becomes infinite, and our current equations simply break down, returning nothing but nonsensical answers. The leading candidate to solve this crisis is string theory. It proposes a breathtakingly elegant idea. The fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy or strings. Just as a single violin string can vibrate at different frequencies to produce every note in a symphony, a single fundamental string can vibrate in different modes to create every particle we see. One specific resonance might correspond to an electron, another to a quark, and crucially, one particular vibration would correspond to the graviton, the hypothetical quantum particle that carries the force of gravity. In this framework, gravity is no longer a mysterious curvature, but just another force mediated by a particle, seamlessly integrating with the quantum world. Another profound approach is loop quantum gravity. If string theory changes the actors on the stage, loop quantum gravity changes the stage itself. It proposes that space is not a smooth, continuous backdrop, but is woven from a fabric of finite, tiny, interconnected loops. Picture the fabric of spacetime as a mesh shirt, a network of a billion threads. These threads are the smallest possible units of space, a quantum of volume. This granular structure prevents the infinite densities that plague general relativity. In this view, the Big Bang was not the beginning of everything but a great bounce. A previous universe collapsed, but when it reached the maximum density allowed by this quantum fabric, it bounced outward, creating our expanding cosmos. A black hole singularity is similarly replaced by a dense but finite core of spacetime threads. The challenge with both of these brilliant ideas is that they are currently almost impossible to test. The energy levels required to see the granularity of space or the vibration of a string are trillions of times beyond the reach of our most powerful particle colliders. We are like musicians trying to hear a symphony playing in a city 1,000 miles away. We must search for indirect clues, perhaps in the faint afterglow of the Big Bang or in the precise timing of distant pulsars. Until we find a way to peer into this quantum realm of gravity, the deepest workings of the universe will remain just beyond our grasp. Crossing the boundary of a black hole is a one-way trip into the future, forced upon you by the extreme gravity of the singularity. But what if you could steer that journey, choosing your destination in time? The laws of physics, as we currently understand them, do not forbid traveling to the future. In fact, you are doing it right now at a rate of 1 second per second. To leap ahead more dramatically, you simply need to exploit a feature of Einstein's special relativity called time dilation. The faster you move through space, the slower you move through time relative to someone who is stationary. Imagine an astronaut embarking on a journey at 99.9% of the speed of light. From their perspective, the flight might only take a few years, but when they return to Earth, they would find that centuries or even millennia had passed for everyone they once knew. This is not science fiction. We have confirmed this effect with ultra-precise atomic clocks on airplanes, which tick ever so slightly slower than their counterparts on the ground. Gravity also warps time, as described by general relativity. A clock at sea level closer to Earth's mass ticks slower than a clock on a mountaintop. So to travel to the future, you have two options: go incredibly fast or park yourself near an incredibly strong gravitational field like a black hole. The future is, in a very real sense, a destination you can reach. The past, however, is a fortress guarded by paradox. The most famous is the grandfather paradox. What if you traveled back in time and prevented your own grandfather from meeting your grandmother? This would create an impossible logical loop. You would never be born, therefore you could never go back in time to stop the meeting. The universe cannot tolerate such a contradiction. So how could backwards time travel even be theoretically possible? The most common proposal involves wormholes, hypothetical tunnels through the fabric of spacetime that could connect two distant points or even two different times. If you could stabilize a wormhole and drag one mouth of it at near light speed while keeping the other stationary, time dilation would cause the two ends to fall out of sync. The moving mouth would become a gateway to the past relative to the stationary one. You could then step through and arrive at a moment before you left. Another theoretical pathway is a closed time-like curve, a path through warped spacetime that loops back on itself, allowing an object to return to its own past. These could exist in the region around a spinning black hole, where the rotation drags spacetime itself into a whirlpool. But all these ideas lead directly back to the problem of paradox. To resolve this, physicists have proposed some ingenious rules. The Novikov self-consistency principle suggests that the universe simply will not allow paradoxes to happen. Any action you take in the past was always part of history. If you try to shoot your grandfather, your gun will jam, or you will miss, or you will have a sudden change of heart. The timeline is fixed and immutable, and your free will is an illusion when it comes to altering established events. This is the model used in films like 12 Monkeys, where the protagonist's attempts to change the past only ensure that it happens exactly as it always did. A different solution comes from the many worlds interpretation of quantum mechanics. In this view, the moment you arrive in the past, you split the timeline, creating a new parallel universe. In this new branch, you can indeed prevent your grandfather from meeting your grandmother. You will never be born in that universe, but that is fine because you originated from a different one entirely. Your actions do not erase your own history. They simply spawn a new, alternative future where you do not exist. This is the chaotic, branching model seen in Back to the Future, where Marty McFly's interventions create a shifting present. While these ideas are intellectually thrilling, they remain firmly in the realm of theory. The energy required to create and stabilize a wormhole is astronomical, and we have no evidence that closed time-like curves actually exist in nature. The past appears to be a castle with a drawbridge permanently raised, its secrets protected by the unyielding laws of cause and effect. Amid the silent, static hiss of the cosmos, a single, powerful scream once pierced the noise. On August 15, 1977, an astronomer named Jerry Amon was reviewing data from the Big Ear radio telescope at Ohio State University. The system routinely scanned the sky, its printouts a long, monotonous scroll of numbers and letters representing the faint radio whispers of the universe. But on that night, Amon's eyes locked onto a sequence so extraordinary that he circled it in red pen and wrote a single, emphatic word in the margin. Wow, the sequence was 6 characters, 6EQUJ5. This cryptic string was not mere noise. It represented a signal that was both strong and narrowband, concentrated on one specific frequency, the exact kind of signature we would expect from an engineered extraterrestrial transmission. For 72 glorious seconds, this signal bloomed in intensity and then vanished, never to be heard again. The wow signal seemed to be a perfect candidate for a message from the stars, a cosmic hello that came and went in less than a minute. The intensity of the signal, captured in that alphanumeric code, peaked at a level 30 times louder than the background noise of deep space. Its frequency was tuned to 1420 MHz, a quiet channel protected by international agreement, a band where earthly transmitters are forbidden to broadcast, right in the zone where hydrogen, the most common element in the universe, naturally resonates. It was as if someone had shouted our name on our own home frequency. Yet, despite decades of dedicated searches pointed at the same patch of sky in the constellation Sagittarius, the silence has been absolute. No echo, no repetition, nothing. This enduring mystery has forced scientists to propose every possible natural explanation. Could it have been a signal reflected off a piece of space debris? The likelihood is vanishingly small, as no known satellite or bit of junk matches the signal's precise characteristics. Perhaps it was a cometary outburst, but the specific comets proposed were not in that region of the sky at that time. Maybe it was an unknown astronomical phenomenon, a brief, natural cosmic burp we have yet to catalogue. but the signal's artificial profile, its narrow focus, makes it a very poor fit for any known stellar event. Each natural explanation seems to fray at the edges, failing to fully account for what the Big Ear telescope recorded that summer night. The tantalizing possibility remains that the WOW signal was exactly what it appeared to be, a one-time beacon from a distant civilization. Perhaps it was a targeted message aimed at another star that we simply drifted through, like a ship passing through a stationary searchlight. Or maybe it was a fragment of a broader transmission, a single, coherent packet in a vast stream of data of which we only caught a fleeting glimpse. It could have been a test, an accident, or a monument, a signal from a species that has long since turned inward or vanished. The circled characters on that old printout are a permanent question mark, a ghost in the machine of our search for company. It is a reminder that the universe might not be perpetually silent, but merely speaking in whispers we are not yet equipped to hear. That fleeting signal teases us with the possibility of cosmic company, but the universe is filled with structures whose origins are almost as mysterious. How do galaxies form? We see these vast islands of stars, these majestic spirals and glowing ellipticals, scattered across the cosmos, yet the precise chain of events that built them from a nearly uniform primordial soup remains one of astronomy's grandest challenges. The story begins with dark matter, the invisible cosmic scaffolding that makes up the bulk of a galaxy's mass. In the early universe, slight fluctuations in density, tiny ripples imprinted from the Big Bang, created regions where dark matter was ever so slightly more concentrated. These over-dense patches had stronger gravity, pulling in more dark matter and the normal hydrogen and helium gas that filled the young cosmos. Over hundreds of millions of years, these dark matter halos grew, forming vast, invisible gravitational wells. The normal matter, the gas that would eventually become stars, simply flowed into these pre-existing pits of gravity, settling into the swirling disks and central bulges we recognize as galaxies. Without this dark matter framework, the universe would have remained a formless haze, its gravity too weak to overcome the expansion of space and pull itself together. Our most powerful supercomputers run simulations of this process, attempting to recreate the universe from its first moments to the present day. These virtual cosmoses are governed by the precise laws of physics we have encoded, and they do produce galaxies. Yet, they consistently get key details wrong. The simulations often create galaxies that are too massive in their centers, or they predict the existence of many more small satellite galaxies than we actually see orbiting large galaxies like our Milky Way. There is a clear disconnect between our theoretical understanding and the actual galactic zoo we observe. The most profound insights are now coming from the James Webb Space Telescope, which acts as a time machine, peering back to an era when the first galaxies were just being born. Its stunning deep-field images reveal a universe that is shockingly mature. We see fully formed, massive galaxies at a time when our models suggested the cosmos should still be in its chaotic, formative stages. These ancient galaxies are not the small, fragile proto-galaxies we expected. They are large, structured, and filled with stars, appearing far too early and too evolved for our standard timeline of cosmic evolution. It is as if we opened a history textbook to a chapter about the Dark Ages and found a photograph of a bustling, modern city. This discrepancy forces a fundamental question. Did galaxy formation start much earlier than we thought, driven by processes we do not yet understand? Or is our model of the early universe and the role of dark matter within it missing a crucial piece of the puzzle? Each new image from Webb is not just a beautiful picture. It is a direct challenge, a piece of evidence from the cosmic crime scene that compels us to rethink the very story of how the largest structures in our universe came to be. Stephen Hawking's great insight revealed that black holes are not entirely black. They slowly leak, evaporating over eons through a quantum process now known as Hawking radiation. This radiation arises from the turbulent quantum fields just outside the event horizon, where pairs of virtual particles constantly flicker into existence. Usually, these particle and antiparticle pairs annihilate each other almost instantly, but at the black hole's precipice, one particle can fall in while its partner escapes, carrying away a tiny bit of the black hole's energy. Over trillions of years, this process would cause the black hole to shrink and ultimately vanish. The paradox sharpens here because Hawking radiation is purely thermal. It is random noise like the heat radiating from a stove. It carries no specific details, no fingerprints, no information about the countless stars, planets, or books that may have fallen in. If the black hole evaporates completely, all that intricate quantum information seems to be permanently erased from our universe, a direct violation of a sacred quantum law that states information can never be truly lost. This is the black hole information paradox in its most devastating form. To resolve this, physicists were forced to consider an even more radical idea, the firewall paradox. If information is to be preserved, perhaps it is not lost inside, but is instead violently released at the event horizon itself. Imagine crossing that threshold, not into empty space, but into a searing wall of high-energy particles, a firewall that would instantly incinerate anything falling in. This solves the information problem by encoding the data into the fiery blast, but it completely contradicts Einstein's general relativity, which assures us that crossing the event horizon should be an uneventful, smooth passage. You cannot have both the gentle fall predicted by relativity and the information-preserving firewall. You must choose one, shattering our understanding of physics at the horizon. Recently, a fascinating compromise has emerged from complex calculations using the gravitational path integral, a tool for summing over all possible histories of spacetime. The solution appears to involve what physicists call islands. These are not physical islands in space, but regions inside the black hole's event horizon whose quantum information becomes, counterintuitively, entangled with the radiation leaking out far beyond the horizon. As the black hole evaporates, more and more of its interior becomes connected to the outside Hawking radiation through this quantum thread. In the final stages of evaporation, the entire information content of whatever fell in is not inside the tiny remnant, but is instead encoded in the intricate correlations within the radiation itself. Think of the black hole not as a sealed vault, but as a cosmic computer that is actively processing and backing up its data to an external cloud, the Hawking radiation. The information was never truly inside in the way we thought. It was always being mirrored, scrambled, and preserved in the radiation field. This means the event horizon might not be the ultimate boundary we imagined, and the interior of a black hole could be profoundly connected to its exterior in a way that saves quantum mechanics without needing a destructive firewall. The fate of quantum information appears to be a cosmic sleight of hand, a preservation so clever that it happens everywhere and nowhere at once, forcing us to rewrite our most basic ideas about space, time, and reality itself. But what if the very rules of the game are not fixed? We have built our entire understanding of the cosmos on one unshakable foundation, the assumption that the laws of physics are the same everywhere and for all time. Yet a series of meticulous observations are now testing this bedrock principle, suggesting that one of nature's fundamental numbers might not be so constant after all. This number is the fine structure constant, often denoted by the Greek letter alpha. It is a pure, dimensionless value that governs the strength of the electromagnetic force. It controls how tightly electrons bind to atomic nuclei, the energy levels within atoms, and the very nature of chemistry itself. If alpha were even a few % different, the delicate nuclear reactions inside stars would fail, carbon would never form, and the universe would be incapable of creating life as we know it. For decades, we have measured alpha in laboratories across Earth and throughout the solar system, and it has always been the same. But when we look to the far reaches of the universe, the story may change. Astronomers have turned the most powerful telescopes toward incredibly bright, distant objects called quasars. These are active galactic nuclei, beacons powered by supermassive black holes whose light has traveled for billions of years to reach us. As this ancient light passes through vast clouds of interstellar gas, specific elements like iron, magnesium, and nickel imprint a unique barcode of absorption lines onto the spectrum. The precise spacing of these lines is exquisitely sensitive to the value of the fine structure constant. When scientists analyze these cosmic barcodes, they find a tantalizing and deeply puzzling signal. The data suggests that billions of years ago, and in certain directions of the sky, the value of alpha was minutely different. Imagine a map of the entire sky. In one vast hemisphere, the measurements indicate alpha might have been slightly smaller in the past. In the opposite hemisphere, it might have been slightly larger. This is not a uniform change across the cosmos, but a potential dipolar variation, a direction-dependent tweak to one of reality's most fundamental settings. If this finding holds, it would shatter a cornerstone of modern science, Einstein's principle of relativity, and indeed all of theoretical physics, rests on the idea of uniformity. The force of electromagnetism that powers the device you are using right now is supposed to be identical to the force at work in a galaxy 10 billion light-years away. If the fine structure constant can vary across space and time, then our entire cosmic map is drawn on shifting sand. The implications are staggering. It could mean that the universe is far larger and stranger than we thought, and that what we call the laws of physics are merely local bylaws, relevant only to our particular cosmic neighborhood. It might provide a pathway to unify the forces of nature, suggesting that what we perceive as separate constants were joined in the early universe and have been slowly evolving ever since. Or it could point toward the existence of extra dimensions, with the variation in alpha being a subtle echo of their hidden geometry. The scientific community remains cautious, tirelessly checking for systematic errors or other mundane explanations. But the possibility alone forces a profound shift in perspective. We are not just mapping galaxies and stars, we are testing the immutable constants of reality itself, asking whether the universe truly plays by one set of rules or if the rulebook is still being written. These silent giants anchor the heart of nearly every large galaxy we see. Our own Milky Way spins gracefully around Sagittarius, a star, a supermassive black hole with a mass 4 million times that of our Sun. The sheer scale is difficult to grasp. The event horizon of this monster, the point of no return, is so vast it could comfortably swallow our entire solar system. Yet this cosmic titan is dwarfed by others. Some galaxies harbor black holes billions of times more massive than our Sun. The greatest puzzle is not their existence but their timing. We see these behemoths fully formed in the early universe when it was less than 1 billion years old. They grew to impossible sizes in what seems like a cosmic blink of an eye. How did they get so big, so fast? This is the great seed problem. What was the original speck that started this incredible growth? One theory is that they began as the collapsed cores of the universe's very first stars. These population 3 stars were giants, hundreds of times more massive than our Sun, and when they died, they could have left behind black hole seeds weighing perhaps 100 solar masses. But there is a problem. Even if such a seed ate material at the maximum possible rate, a process limited by the physics of accretion and radiation pressure, it would not have had enough time to balloon into the supermassive giants we observe so early on. The math simply does not add up. Another possibility is a more direct path, skipping the star phase entirely. In the chaotic dawn of the cosmos, vast clouds of primordial gas could have collapsed under their own immense gravity, directly forming a massive black hole seed tens of thousands of times heavier than our Sun. This gives the growth process a huge head start, a seed already large enough to rapidly consume the gas-rich environment of the young galaxy. The James Webb Space Telescope is now searching for evidence of these direct collapse black holes, looking for the unique signature of gas falling into a massive, dark object without the brilliant light of a star at its core. Then there is the most exotic idea of all. Perhaps these seeds are not made of normal matter at all, but are primordial black holes forged in the unimaginable density and pressure of the Big Bang's first moments. In that seething furnace, random fluctuations could have compressed pockets of space so intensely that they pinched off into tiny, yet incredibly dense black holes. Over billions of years, these primordial relics could have served as the nuclei around which galaxies themselves formed, growing in lockstep with their cosmic homes. The mystery of their origin is inextricably tied to the birth of galaxies themselves. Did the black hole form first, its gravity pulling the galaxy into being around it? Or did the galaxy form first, funneling a feast of gas to a small seed at its center? The answer is likely a complex dance, a feedback loop of gravity and growth that we are only beginning to understand. Buried within the faint, cold glow of the universe's first light is a pattern that should not exist. This light is the cosmic microwave background, the ancient afterglow of the Big Bang itself. It is a snapshot of the infant cosmos, a mere 380,000 years old, when it had cooled enough for atoms to form and light to travel freely. This background radiation is the most perfect blackbody spectrum in nature, a nearly uniform curtain of microwave light that fills every direction of space. According to our most cherished cosmological models, this glow should be statistically isotropic, meaning its tiny temperature fluctuations should be randomly distributed with no special direction or axis. The universe should have no preferred left or right, no up or down on its grandest scale. Yet, when we map this primordial light with extraordinary precision, using instruments like the Planck satellite, we find unsettling anomalies. There are strange, large-scale alignments in the data, a mysterious directional preference that has been nicknamed with a hint of dramatic flair, the axis of evil. One of the most prominent features is a curious alignment of the largest temperature fluctuations. The quadrupole and octupole moments, which describe the biggest waves in this cosmic sea, appear to be strangely coordinated, their hot and cold spots pointing in the same general direction across the sky. It is as if the entire universe has a slight tilt, a fundamental lopsidedness imprinted at its birth. Furthermore, there is a perplexing hemispheric asymmetry. One half of the sky shows significantly more pronounced temperature variations than the other, a cosmic imbalance that defies the principle of uniformity. There is even a mysterious cold spot, an unusually large and deep patch of coolness that is incredibly difficult to explain through standard physics alone. So what could this mean? The most conservative explanation is that we are simply seeing a statistical fluke. With a universe as vast as ours, even the most improbable patterns can appear by pure chance in one particular vantage point. Perhaps the axis of evil is just a cosmic mirage, a trick of the light that will vanish with more precise data. Another possibility is that it is not a feature of the cosmos, but an artifact of our own measurement. Maybe there is an unknown foreground contaminant within our own solar system or galaxy, a local fog that is distorting our view of the primordial sky. The most thrilling and disquieting possibility is that the axis of evil is a genuine crack in our standard model of cosmology. It could be a fossil, a relic from a time before the Big Bang, a signature of something that influenced our universe from the outside. Perhaps it is an imprint from a collision with another universe in the multiverse, or evidence that the cosmos is not infinite and uniform, but has a complex, topologically twisted shape that we are only just glimpsing. The Planck satellite's map of the cosmic microwave background, with its beautiful, mottled splendor, is therefore more than just a picture of our origins. It is a cryptic message, a cosmic riddle written in the language of temperature and light. The axis of evil challenges our most basic assumptions about the universe's symmetry and independence, forcing us to ask if our entire cosmic history is written on a slightly skewed page. Even the most meticulous plans can reveal a subtle, persistent drift. For years, as the Pioneer 10 and 11 spacecraft journeyed beyond the planets, navigators noticed something was wrong. These robotic pioneers, the first human-made objects on a trajectory to leave our solar system, were not quite where our models predicted they should be. An almost imperceptible force was acting upon them, a tiny but constant deceleration back toward the sun. It was as if a ghostly hand was gently applying the brakes, a force 80 billion times weaker than gravity on Earth but unrelenting. This was the Pioneer anomaly. For decades, it was a quiet thorn in the side of physics. Could it be a sign of new physics, a flaw in our understanding of gravity itself at the vast scales of interstellar space? Perhaps dark matter was exerting a local drag, or our knowledge of the solar system's mass was incomplete. The anomaly was so small it could be dismissed as a curiosity, but its persistence made it impossible to ignore. It represented a tiny crack in the foundation of our cosmic understanding. The solution, when it finally came, was not from a revolutionary theory, but from meticulous detective work and a surprising source of pressure. The culprit was heat, but not from the sun. The spacecraft were powered by radioactive thermoelectric generators, and these units emitted a steady, faint warmth. While this heat radiated evenly in all directions, the spacecraft itself was not symmetrical. Its large, parabolic dish antenna acted as a shield, reflecting more heat forward in the direction of travel than backward. This created a tiny imbalance, a minute push from the photons of infrared light. Every single photon carried a minuscule amount of momentum, and the net effect of billions of them was a constant, gentle pressure backward, exactly mimicking an additional pull from the sun. It was the spacecraft's own warmth slowly pushing it off course. The Pioneer anomaly stands as a powerful lesson in cosmic humility. It shows us that the universe's greatest secrets can sometimes hide in the smallest, most overlooked details. A discrepancy 1/10 billionth the force of gravity was enough to spark a decades-long investigation. It forces us to ask what other tiny anomalies we are currently ignoring, what other whispers in the data we are dismissing as noise. Our most precise instruments are now measuring the cosmos with ever greater fidelity. What if the next anomaly is not a trick of thermal engineering, but a genuine signal from beyond our current physics, a tiny crack that, when pried open, reveals an entirely new layer of reality? Ultimately, the question of why we exist at all seems to circle back to a void. Can the universe, in the most profound act of self-creation, have summoned itself from absolute nothing? This is not about a quantum field or a pre-existing vacuum, but a true nothing, no space, no time, no laws, no potential. The concept is almost impossible for our minds to hold. Modern physics offers a startlingly elegant, though deeply challenging, answer. The total energy of the universe might precisely equal zero. Every bit of positive energy bound up in stars, planets, and our own bodies is perfectly cancelled out by the negative gravitational energy stored in the fabric of space itself. Think of the cosmos as a vast, intricate loan. The matter and light we see is the positive balance, while the stretching of space-time is the cosmic debt. They sum to nothing. In this view, our entire universe could be a single, magnificent quantum fluctuation that simply popped into existence, borrowing energy from the void, and because the total is zero, never having to pay it back. It would be the ultimate free lunch. The physicist Lawrence Krauss describes this as a universe from nothing, where the unstable nothingness of a quantum gravity vacuum spontaneously spawned everything we know. But this immediately confronts a philosophical wall. Is this quantum vacuum with its laws and fields truly nothing, or is it just a different kind of something? The nothing described by physics is a seething arena of potential governed by quantum rules. The nothing of philosophy is the utter and complete absence of anything, including laws and potential. Which is the more profound foundation for reality, a self-creating quantum system, or a true, featureless nothing from which such a system could never logically emerge? We are left staring into an abyss of definitions. Does the universe need a creator, or is the very concept of a creator dependent on the existence of the universe? Perhaps the only way to have a universe with no supernatural strings attached is for it to be its own cause, a self-contained loop of existence where the question of what came before simply dissolves. The cosmos might not have an external origin story. It might just be a necessary, self-consistent, and breathtakingly beautiful fact. Our most precise cosmic measurements are now in direct conflict. We have two master keys for unlocking the expansion rate of the universe, a number called the Hubble constant. Each method is incredibly sophisticated, each has been refined over decades, and each gives a different, stubbornly irreconcilable answer. This growing discrepancy is the Hubble tension, and it is a crack in the foundation of modern cosmology. The first method peers into the deep past using the cosmic microwave background. This ancient light from the infant universe carries a detailed imprint of its early conditions. By analyzing the subtle patterns of hot and cold spots in this radiation, scientists can calculate how fast the universe was expanding just after the Big Bang. Using our well-tested model of cosmic evolution, they can then run the clock forward to predict what the expansion rate should be today. This is a top-down approach, starting with the baby picture of the cosmos and predicting its present state. The second method works from the bottom up, measuring the universe's current expansion directly. Astronomers observe Type 1a supernova, those standard candles in distant galaxies, to gauge distances. They also use pulsating stars called Cepheid variables and other local markers. By comparing these distances to how fast the galaxies are moving away from us, measured by the reddening of their light, they get a direct read on the Hubble constant here and now. The problem is the numbers do not match. The prediction from the early universe is consistently slower than the direct measurement from the local cosmos. It is not a small error or a margin of miscalculation. It is a persistent, statistically significant gap that has only widened with more precise data. Imagine two groups of master clockmakers. One group studies the universe's original blueprints from 14 billion years ago and builds a clock that they are certain should tick at a specific rate. The other group uses the most advanced tools to measure the ticking of the actual cosmic clock all around us. Both groups are supremely confident in their work, but their clocks tick at undeniably different speeds. This is not a simple mistake. It suggests that our standard model of cosmology, the lambda cold dark matter model that has been so successful, might be incomplete. Perhaps dark energy is not constant but is evolving, growing stronger over time and pushing the expansion to accelerate faster than our models allow. Or maybe dark matter has properties we have not yet accounted for, interacting with itself or with light in strange ways. There is even the extraordinary possibility that the universe is not as uniform as we think, that we live in a local void, a cosmic bubble where the density of matter is slightly lower, making our local measurement of expansion atypically fast. Each potential solution points toward new physics, a deeper layer of cosmic reality that we have not yet grasped. The Hubble tension is more than a technical disagreement. It is the universe presenting us with a paradox, challenging us to look closer and think deeper about the forces that truly shape our cosmic home. Our journey through the cosmos has brought us to a final, dizzying precipice, a question that dissolves the boundary between physics and philosophy. If we peel back all the layers of reality past quarks and quantum fields, what remains at the absolute foundation? The mathematical universe hypothesis offers a radical answer. Our physical world is not just described by mathematics, it is mathematics. Every galaxy, every person, every fleeting thought is part of a vast, abstract mathematical structure. In this view, the universe doesn't just run on numbers like a computer simulation. It is the numbers. The atoms in your hand are not merely obeying mathematical laws. They are physical instantiations of those laws, temporary patterns in an eternal equation. This idea extends to its ultimate conclusion, leading to the level 4 multiverse. If our reality is one specific mathematical structure, then every other self-consistent mathematical structure must also exist somewhere. Every possible variation of physical laws, every conceivable geometry for space and time, every bizarre universe where gravity is repulsive or time runs in loops, they are all equally real. They are not elsewhere in our space, but are other mathematical landscapes entirely, just as valid as our own. This forces a profound question about the nature of consciousness. If our minds are simply complex computations running on the wetware of our brains, then they too are mathematical patterns. And if that is true, then any sufficiently complex mathematical structure would contain self-aware substructures, conscious beings who perceive themselves as living in a real world. Your own sense of being might be one such pattern, a knot of self-awareness woven into the cosmic calculus. Picture the intricate, infinite swirls of the Mandelbrot set, a shape of infinite complexity generated from a simple equation. Zooming into its boundary reveals an endless parade of unique formations, each one a perfect, self-contained world of geometry. The mathematical universe hypothesis suggests our cosmos is like one of those formations, a single pattern in an infinitely larger mathematical fractal. We are not just looking at the fractal, we are a tiny, temporary part of it, a fleeting arrangement that has become aware of itself. This is where our exploration ends, not with an answer, but with the most profound mystery of all. Are we physical beings discovering abstract mathematical truths, or are we abstract mathematical truths for a fleeting moment believing ourselves to be physical? These 30 questions are not a map of our ignorance, but a testament to our ambition. Each mystery, from the silent darkness between stars to the paradoxical heart of a black hole, is a frontier. Science is not a dusty collection of answers, but a living, breathing quest for understanding. The absence of a final answer is not a failure, it is the very engine of discovery. It is the blank space on the map that calls the greatest explorers. This pursuit, this relentless collective curiosity, is what transforms us from passive inhabitants of the cosmos into active participants in its grand story. So the next time you find yourself under a clear night sky, look up. Let your eyes trace the faint band of the Milky Way, find a distant, shimmering point of light, and remember that you are looking at the greatest puzzle ever conceived. You are part of a species brave enough to ask and resilient enough to keep searching when the universe answers with a deeper, more beautiful question. We want to know which of these cosmic riddles captivates you the most. Share your favorite unanswered space question in the comments below. And if this journey to the edge of knowledge sparked your wonder, subscribe to join us as we continue our deep dives into the cosmos. The universe is waiting.